Here in Victoria with me, Martin Davis, one of three Victoria speakers today, amazingly. We are all members of the Victoria Geospatial Mafia, which I get to talk about at the end of PostGIS Day.
Hey, Paul.
Hi, Martin. And yes, we got everything here. We got a little bit of H3 going on. We got a little tile surf going on. I assume you'll be talking MapLibre a little bit for us.
A little bit, yeah.
Yeah.
Yeah, every hip geospatial conference needs to have an H3 talk, and I'm the lucky guy that gets to be the H3 guy today.
All right. Well, I'm just going to let you take it away. We'll start a minute early.
Okay, let me just share my screen here. All right. Can you see slides?
Oh, wait, I'm probably not looking at the right thing.
Not yet.
No, I'm not seeing slides either.
Hang on, hang on.
Oh, here we go. Yep, that did it.
Got it. Okay. Well, good afternoon, everybody. I am going to talk today about using PostGIS and H3 to analyze UFO risk. I got a problem here. Oh, there we go. One potential problem with the green transition is that there's more and more wind turbines out there. And as we know, there's lots of UFOs floating around too. So what happens if UFOs collide with wind turbines? So we are going to use PostGIS and H3 to figure out where that might happen. So what I'm going to talk about today is what is H3 and why do you want to use it or not use it? We'll talk about the H3 API and an extension called H3PG that lets you use it in Postgres. We're going to show how to build a UFO risk dashboard with PG TileServe and MapLibre. And then we're going to experiment with some different visualization techniques, such as heat maps, H3 clustering, H3 tiling. And finally, we're going to analyze the UFO risk to wind turbines using H3. So what is H3? It is a multi-resolution hexagonal global grid system with hierarchical indexing. It was developed by Uber to enable global scale analysis. It's a grid of hexagonal cells that cover the globe. Mostly, there's actually 12 pentagons cleverly spaced around the globe in the water, mostly. There's 16 different grid resolutions, which go from 4.3 million kilometers per cell down to 1 square meter per cell. So any resolution you can imagine. And the cells are roughly hierarchical. One cell at one resolution refines into 7 cells in the next. Each cell has a unique 64-bit index, which is quite handy, and I'll talk about that in a sec. And there's an extensive API that let you work with cells, IDs, and geometries. So before we talk about why H3, we got to talk about why would you want to grid your data in the first place? Well, gridding provides a common basis for analyzing data. That lets you do multivariate analysis, and it lets you easily analyze all kinds of spatial data types, points, lines, and areas together. Grids, because they're aerial, inherently provide feature density, and they make it very fast to compute spatial joins and overlays. For display purposes, they reduce data size, so that leads to faster transfer and display, and it lets you use a uniform styling. So why H3? Well, it's a standard grid for global data sets, which makes it easy to combine different data sets. Equal area cells across the globe are good for data analysis. It's hard to get that with square grids because in the poles, square grids typically get much smaller. Cell neighbors are equidistant, which means there's fewer edge effects and you can better represent paths through the grid. Grids are independent of human and natural boundary variation. The cell IDs provide fast indexing and joining. There is a powerful API, and H3 is widely supported across a lot of different platforms. So why would you not want to use H3? Well, because it doesn't follow human or natural boundaries. Sometimes you may want to have something that better reflects those kinds of boundaries. It's geodetic only. It doesn't work with planar coordinate systems. You might have to transform or clip your data to get it into H3. The cells at different resolutions don't exactly nest, although that's not really a big problem in practice. Hexagonal cells are a little more complex than square grids. And of course, you need access to the H3 API. But luckily that H3 API is widely available now. There's lots of different bindings to languages. It's available on lots of platforms such as Postgres, DuckDB, Snowflake, et cetera, et cetera. For Postgres, there's an extension called H3PG, which is a Postgres extension with about 80 or more than 80 functions. And it's well integrated with PostGIS. So as an example, here's some H3PG functions. There's a function called H3 lat long to cell. And if you give that a geometry, it returns the index of a cell for the point in the geometry. You can go the other way. You can give a cell index and get a hexagonal geometry back. And you can directly compute things like cell area just from the index. You don't actually have to create the geometry in order to get areas. And there's lots of other functions, but actually just these three functions are going to let us do everything that I'm going to show today. So for data, we're going to use a data set of UFO sightings, which has got about 60,000 points in it, and a data set of wind turbines, which is about 64,000 points. The URLs for them are there. I won't talk about how to load them into PostGIS. That's pretty straightforward. So once we've got the UFO sightings loaded, we can visualize it through PG tile serve. That just pops up automatically, and we get tiles out showing all 60,000 points. And we can do the same thing with the wind turbines. But obviously just seeing them in the tile serve UI, it'd be much nicer to have a custom UI where we can do things like style them. So we're going to build a UFO Risk dashboard. We're going to use PostGIS and H3PG on the back end. We're going to use PG tile serve and feature serve. And we've built a simple web app with HTML and MapLibre and just a sprinkling of JavaScript. And this code is all available in a GitHub repo. You can see the link at the bottom of the screen. So I'm going to show quickly what displaying the raw data points looks like in the dashboard. So you can see that's pretty quick, but for more points, it would slow down. And just seeing a mass of points isn't all that useful. For instance, it's hard to tell, are there UFOs that are close to wind turbines and how many? So that's what we're going to dig into next. We're going to show different ways of visualizing the actual UFO point data. And we're also going to show how to do some analysis using H3. I think I just skipped over one. So one way you can visualize point data, of course, is with heat maps. Sorry, Brian. This is a MapLibre client-side heat map that I'm showing here. The problem with that is it needs access to all the data points. So it can handle 60,000 data points, but if you had 600,000 data points, it would be too slow to use. Plus, you don't get good statistics out, and you can really only visualize a single variable. So another way to visualize is to use H3 clustering. And this is where we start getting clever. We're going to show how to use a PG tile serve function to produce the display that you're seeing there. So we're going to group data points by H3 cell ID based on the zoom level of the map. We're going to compute the number of points in the cell, and then we're going to display them via PG tile serve. So the advantage here is it's server side. It's very fast to compute the clusters. It produces small MVT tiles. And by using H3, you get a natural looking distribution of points. So as Elizabeth mentioned, in PG tile serve, you can actually create custom functions to produce map tiles. So what we're going to do is we're going to make a function that takes the UFO point data and turn it into H3 hexagons based on the zoom level with a count of the number of UFOs in each hexagon. So this is what the function looks like. I'm going to zip through here. This is all in the GitHub repo. Basically, we aggregate all the points by their H3 cell ID. And we're going to do that just for the tile that's being produced. And then we're going to generate the MVT geometry and the MVT tile. This is just basically standard boilerplate for creating a PG tile serve function. So here's the raw data being shown in tile serve, so you can see that it only shows a few points at a fairly large zoom level. And now we're going to see what that looks like in dashboard live. So you can see, I'm going to turn on the UFO sightings just to start with, and then we're going to add clusters on top of that. So you can see the clusters are very fast. Because they're fast to compute on the server side, and you're only shipping a few points per tile down. This is actually a relatively small data set. I've tried this with a data set of about 2 million points, and it's it works quite performantly. You could also cache these tiles too to make it even faster. There we go. Okay, so clustering is pretty nifty, but it doesn't necessarily give us a great idea of the density of UFO sightings. So another way we can do it is display them as H3 tiles. So this is very similar, except instead of computing clusters, we're actually going to compute the hexagonal tiles for the UFO points. So here's a similar function. I'm just showing the code to, in this case, the points are grouped by their H3 cell ID, and then the cell ID of each grouping is used to generate the hexagonal geometry. And then we attach the cell area to that geometry. We can also use that to compute a density value for the cells. And then we can display that in the dashboard. So this is a MVT layer in dashboard being shown by MapLibre. And it's zoom dependent. So as we zoom in, we get denser. We choose a higher H3 resolution, and we get denser hexagons. And the styling is all done in MapLibre, of course. So you have a lot of flexibility with that. Okay, so we've been moving right along here. So now we're going to actually do the UFO turbine risk analysis, which is what we talked about at the beginning. And the way we can do this, those are both point data sets. So to actually combine them so that we can compute a risk value for UFO and wind turbine potential interaction, by mapping both those data sets onto H3 cells, we can then compute a risk value for each H3 cell and then display that on the map. So we're going to assume that the UFO risk is proportional to the UFO density and also proportional to turbine density. I'm not really a spatial analyst, so hopefully that's makes sense in terms of an analytical function for risk. So once again, we're going to build a tileserve function to compute this. We're going to count the UFO sightings and map them to an H3 cell, and we're going to count turbine locations by H3 cell. Then we're going to join both of those data sets, and we can just join on the cell ID. So the join is very quick. There's nothing spatial involved there. And this is all done on the fly, by the way. There's no caching involved and no spatial index either. So then once again, we create the H3 hexagon feature with computing the geometry for the H3 cell and computing the risk value, and then some additional information for each cell. We're also going to create a SQL view for the UFO risk. And we're going to use this in PG feature serve to provide the top hexagons, the top risk hexagons in the dashboard. So here's that view in PG feature serve. It just shows up as a view. We can query it using just a URL. And we can use some of the, a couple of the OGC API parameters to sort the information in a descending way. So we get the highest risk features and we limit it to size 10. We could get the entire collection if we wanted to, but we're only going to show the top 10. So this produces a JSON document that we can just call directly from our web page and show. And we're going to pull this together and show it in the dashboard. So when we turn on the UFO turbine risk, we can see the hexagons that are color themed. Darker is higher risk. You can also see the top 10 risk areas on the left-hand side of the screen. That's being pulled from the PG feature serve query, backed by the view. So as we zoom in, the H3 hexagons get higher resolution. So we can start to identify the areas of highest risk. We'll turn on the actual data points here. But of course, you don't want to have to scan the whole map to find the highest risk hexagons. So that's where the analysis view comes in, the top 10 view. And that'll allow us to zoom to the areas of highest risk. So we can just click on each one of those features and that'll zoom the map. And we're showing this at H3 resolution 6. So this is going to show us areas where you either have a lot of UFOs or a lot of wind turbines or both. We'll show one more here. Just outside Kingman, Route 66. And that's it. I'm a little ahead of time here. Any questions?
So why H3? Why not squares? You just saw some beautiful squares earlier. Well, what's the deal with these?
Well, like I said, H3 is global and it's geodetic, so it provides equal area cells, which you can't really get with a square grid. I think people find it looks a little more natural, although I'm not sure. Yeah, I'm not sure that it's statistically significant, but visually it looks nice. And another big reason is that it has this great API. It's a very complete API. I barely scratched the surface here. So square grids don't really have the equivalent level of support in terms of API, although I think we could potentially build something like that out, maybe in Web Mercator space. I mean, we've got the beginnings of it in PostGIS, but a few more functions, and in particular, having that single cell ID value could be quite handy.
Yeah. People insist on calling H3 an index. You know why that is?
I was thinking of mentioning that. Yeah, I don't know. Maybe because it sounds cool. I guess it sort of is an index, but you're not really using it in that way. Yeah, I think, mind you, the other option is calling it a discrete global grid system, which is a bit of a mouthful. So I also like that too. Like, is there any other kind of grid other than a discrete one? I don't know.
Right. Yeah. Okay. And then I guess the last question would be like, why not a planar? We can do planar hexagons. What's wrong with planar hexagons? At least all the
Uh,
planar hexagons are all hexagons. They don't try to sneak in a dozen pentagons.
Yeah, exactly. Well, of course, planar doesn't work for global level data sets. But for planar coordinate systems, yeah, that would work great. Um, Again, one nice thing about H3 is that it's a standard grid system. Something I didn't show is, I mean, that means that you can actually just download data sets that are already gridded in H3. For instance, Contour has worldwide population data sets. And actually something I didn't show is
Mhm.
I pulled down the Contour population data set in H3, and then I was able to quickly join that to the UFO data set to do an analysis about, you know, where are the UFO sightings where you don't have very many people. So they're a little more significant than ones in downtown LA where you have millions of people.
But when everything is encoded with H3 IDs, can we throw away PostGIS?
I hope not.
Yeah,
Otherwise, we won't be here next year.
it's true.
It'll be H3 day.
H3 day. Everyone will just
Yeah,
be joining their hexagons together.
yeah.
All right. Thank you very much, Martin.
My pleasure.